Hello everyone! In this video we will continue to examine topic 7.1, discrete energy and radioactivity, and in particular we will continue to discuss nuclear physics. In the last video we went through our initial answer, although that's all it was, for why the nucleus does not fly apart due to the electrostatic repulsion between the protons. And the answer was the existence of this nuclear strong force, and in particular the residual strong force, so the leftover strong force that dominates the interaction between the quarks, which are the constituent particles of the nucleons themselves, is the answer to this question. Now, we haven't discussed what our evidence is for this, how the strong force works, any other of the details. In some ways, this is not so much an answer to the question as just a name for an answer to the question, but we will get there in time. The nuclear strong force is the dominant force at the level of the nucleus, in that it binds the protons and neutrons together. But as it turns out, it is not the only force or interaction at the level of the nucleus. We'll return to the strong force later, but in this next subsection, we are going to discuss what is known as the weak nuclear force. And I will say at this point, calling it a force is exceptionally misleading. At microscopic scales, as it turns out, the fundamental theories that underlie sort of what we think about microscopic phenomena are known as quantum field theories. They're fundamentally related to the idea of fields that we introduced in gravitation and electromagnetism. And as it turns out, those fundamental fields are not directly connected to what we would consider to be a classical force at all. Instead, we can think of these microscopic fundamental things that go on as better described as just internal interactions. That is, there are a number of entities, a number of particles that interact in different ways, and those ways have patterns, and we can call some of them strong interactions or weak interactions. Another way of saying this is that when you picture a force, you picture sort of a macroscopic push or pull, and we are pretty far away from that being a good description of what is fundamentally going on. So I prefer the term interaction, in particular for the weak nuclear interaction, in part because force just doesn't make any sense. It's not a straightforward push or pull. It does not lead to a directly calculable acceleration, that kind of thing. The strong nuclear force, to some extent, can be pretty well described as a force, particularly if you're only looking at the residual strong force, but fundamentally it as well is probably better described as just an interaction, a set of things that happen. So, in discussing the weak nuclear interaction, the primary mechanism by which we understand the weak nuclear interaction is radioactive decay. And that's because, at a very fundamental level, the weak nuclear force and weak nuclear interaction governs radioactive decay. What we're going to do in the next subunits is to discuss, first and foremost, radioactive decay. Because as scientists, this is what we discovered first. Radioactivity has been known for a while, and it is only sort of in more recent studies of fundamental physics that we have understood what is going on with respect to the weak nuclear force or interaction. So let's discuss radioactive decay. Radioactive decay is defined as the random and spontaneous emission of particles or high-energy photons from unstable nuclei as they decay from high-energy to low-energy states. Now, there is a lot going on in here, okay? A lot going on in there that we're going to need to discuss and explain over time. So we'll take it bit by bit. radioactive decay is something that happens to nuclei, and in particular to unstable nuclei. Now, stability for nuclei is really a spectrum. The most stable nuclei, we will never see decay in our lifetimes, and the most unstable nuclei decay in a fraction of a second. Now, what do I mean by decay? Decay is a word here that means that they are sometimes transmuting. We'll discuss what that means in a bit, but transforming, changing from one state to another, in particular from high energy to low energy states. And it is important to recognize that when they do so sort of simply going from one state to another. It's not continuous. It's not a slow transformation. At one moment, you have the unstable nuclei, and at the next moment, you have the products of the decay. That is, the results of that decay. But that's not the weirdest part, and we'll talk about that in a bit. The weirdest part is that fundamentally, they are unpredictable and uncaused. Random and spontaneous. Random here just means unpredictable. A particular decay, that is when this particular particle will decay, cannot be predicted. And that is a matter of physical reality, not just because we don't know enough about what's going on. There are a number of experiments that help show this, but take it for granted at this point that what is happening is not a matter of ignorance. It's not because we just don't know enough about what's going on at a microscopic level, that the fundamental laws of quantum field theory, the fundamental laws of physics that govern this phenomenon, have built into them a certain sense of randomness. You see this referred to in pop culture when quantum physics is discussed, and it's really related to the quantum nature of the quantum field theory that underlies radioactive decay. So not only is it unpredictable, it's spontaneous. That is, if we look right before the decay, we can suggest the odds of something decaying, but we cannot say what caused that decay directly. There is no proximate cause. That is, you look right before it was to decay, and it looked no different than just before that. There is no direct, immediate cause or impetus. It happens of its own self. So when you get an instance of radioactive decay, right before the decay, you would not know it was about to happen. And it is completely unpredictable as to whether it would happen or not. Notice these are slightly different ideas. This has to do with, regardless of how it happens, could you predict it, that it would happen? And as it turns out, no, you can't. And this is about the fact that, well, regardless of whether you could predict it or not, could you at least sort of see what led to it? And the answer is no, it's uncaused. It simply happens. Okay? And what happens? Well, these unstable nuclei release particles or high-energy photons. And this is what is known as radioactivity. So radioactivity includes the emission of particles or high-energy photons, that is light or other electromagnetic waves, and this is what was detected. Okay, so we knew about this way before we understood what was going on, and we will discuss radioactivity in more detail shortly. The last incredibly important concept with radioactive decay, I've already alluded to a little bit, but I'm going to emphasize it. This is probably the most important aspect of it, which is that although radioactive decay events are random and spontaneous, that the laws that govern radioactivity are fundamentally probabilistic in nature. So what does that mean? It means that although we cannot predict or say exactly what caused a decay event to happen, we can, with very high degrees of certainty, predict the probability of it happening. Does that mean it will happen? No. Does that mean it won't happen? No. We'll never know that. That is unpredictable. But if we get a huge number of these particles who are about to radioactively decay, and we know the nature of that radioactive decay, then we can predict with a high degree of probability whether any one of them will decay or not. So the individual decay events are unpredictable, but the collective outcome over many decays and over significant time is not. This is fundamentally the same idea as the individual outcome of a coin flip is 50-50, heads or tails. You cannot, I gotta be careful. In ordinary life, you cannot predict that outcome. It could be one, it could be the other, and there's no result of a coin flip that would sort of defy that law. But over hundreds and thousands and millions of coin flips, you would very much expect that you would get roughly 50% heads and roughly 50% tails. If you did not, if you underwent 1 million coin flips and you discovered that with a high degree of certainty, 80% of the time, your coin flip came up heads, then you have learned something new about flipping that particular coin. So what that means is our laws of physics with respect to radioactive decay do tell us a lot. They tell us about these specific probabilities of things going on, even if we can't say anything about an individual decay event. And so one of the keys of investigating radioactive decay is the idea that when we study radioactive decay, we are almost always studying vast collections of particles, many, many particles over significant time, so that we can see this probabilistic nature.